Bernoulli's equation. So let's think about this ideal fluid that is being pushed through this tube. And once again, I have a cross-sectional area A1 here, and pressure at this point 1 is P1. So P1A1 would be the force that is being exerted in I hat direction. So basically, I'm assuming that this is my x-axis. So that's my I hat direction. And as a result, we have fluid particles here that are moving with a tangential velocity v1. And on the other side, there are fluid particles that are exiting here. And in the time interval dt, delta t, they're traveling a distance delta x2. So that's this blue portion. And we have a pressure P2 applied from outside, so minus P2A2 I hat is the force on these particles, and they have a tangential velocity V2 to the right-hand side, and these two sections are at a distance y1 and y2 with respect to ground. So you can see here they're at a distance y1 and here at a distance y2. Okay, so what is the work done on the fluid in segment 1? So we have a force P1A1 I hat, and the fluid particles travel a distance delta x1, so P1A1 delta x1. So that's A1 times delta x1, that's the volume here. So that's going to be a pressure at point 1 multiplied by the volume. What about the work done on the fluid in segment 2? Here we have a force minus P2A2 I hat. The displacement is in positive I hat direction, so delta x2 I hat. So we have minus P2 times V, that is the work done on the fluid in segment 2. Okay, so what is the net work done on this fluid? It is P1 times V minus P2 times V. So it's the same volume that is being displaced. And this net work done by the external force goes into the change in the kinetic energy and potential energy. So that causes a change in the mechanical energy. So if we consider the total mass of the fluid particles in the section there that are moving with tangential velocity v2, 1/2 mv2 square will be the kinetic energy, and then there will be the kinetic energy of the rest of the fluid particles, minus 1/2 mv1 square for the particles that are entering the pipe, and the rest of the particles, kinetic energy of the rest of the particles. So the change in kinetic energy is 1/2 mv2 square minus v1 square. And what about the potential energy? Well, these particles are at a distance y2 with respect to ground, so mgy2 plus the potential energy of the rest, and then here we have mgy1 plus the potential energy of the rest. So the difference is mgy2 minus y1. Okay, so the change in the mechanical energy, delta K plus delta U, change in kinetic plus change in potential energy, is the net work done on this fluid in the pipe. So P1 minus P2 times V, that the net work done is 1/2 mv2 square minus v1 square plus mg y2 minus y1. So if I write this energy equation and multiply it by 1 over the volume, I obtain P1 minus P2 is 1/2 rho V2 square, m divided by V, mass of the fluid particles in the section divided by their volume, that's the density, minus 1/2 rho V1 square, and this will be m over V also, rho Gy2 minus rho Gy1. Okay, so rho is mass divided by volume. Now, if I take this P2 to the right-hand side and V1 square and Y1 terms to the left-hand side, I can see that P1 plus 1/2 rho V1 square plus rho Gy1 is equal to P2 plus 1/2 rho V2 square plus rho Gy2. That means the pressure plus 1/2 rho V square plus rho Gy is a constant. for this fluid. So this is called Bernoulli's equation, and Bernoulli's equation basically is a statement of energy conservation. So that's the net work done by the external agent is equal to the change in mechanical energy of the system. So this equation tells us that as we decrease the pressure, the velocity will increase and also the y will increase. So when at rest, when v is equal to 0, we have p1 plus rho gy1 equals p2 plus rho gy2, or p1 minus p2 is equal to rho g delta y. Okay, so that's basically the Bernoulli equation. Now let's see some examples. The Venturi tube. The horizontal constricted pipe illustrated in the figure is known as a Venturi tube, can be used to measure the flow speed of an incompressible fluid. Remember, incompressible means we have a constant density. All right? So density doesn't change. Determine the flow speed at a point 2 of figure if the pressure difference is known. Okay, so the pressure difference P2 minus P1 is known, and we have cross-sectional area A1 here, velocity of the particles V1. You can see this is laminar flow, and here we have a cross-sectional area A2 and velocity V2. So therefore we have P2 minus P1 known, and we have the cross-sectional areas A1 and A2 known. So what is the flow speed at point 2? V2, that is our question. Now you can see that this is a horizontal arrangement, so when we look at the mass of the particles being at a distance h with respect to the ground, these particles will also have an average distance h with respect to the ground, so we don't talk about the change in the potential energy. So let's write Bernoulli's equation for this setup. Bernoulli's equation tells us that the pressure at point 1 plus 1/2 rho V1 square is equal to pressure at point 2 plus 1/2 rho V2 square, because we don't have a change in the y position, so we only talk about kinetic energy terms here, 1/2 rho V square terms, and pressure. So this gives us P1 minus P2 is equal to 1/2 rho V2 square minus V1 square. So if we rearrange this, 2 P1 minus P2 divided by rho is equal to V2 square minus V1 square. Now, we also have the continuity equation. The continuity equation tells us that the volume flux is a constant, so cross-sectional area 1 times volume 1 dV dt is equal to A2 V2. This is a statement of the continuous volume flux. So this allows us to write V1 in terms of V2. So V1 is A2 V2 divided by A1. So we can substitute this result for V1 into this equation, and we will obtain 2 P1 minus P2 divided by rho is equal to V2 square minus, for V1 I'm substituting this result, A2 over A1 squared V2 squared. So this is basically 1 minus A2 over A1 parentheses squared V2 squared. So this allows us to write V2 as 2 P1 minus P2 divided by rho A1 square minus A2 square multiplied by A1 square, and then we have the square root. Alright, so this is our final answer for V2. So here we have utilized both the energy conservation, Bernoulli's equation, with no change in the potential energy, and continuity equation, the volume flux is a constant, and this allows us to write V2. Okay, let's look at another example. Toricelli's law. An enclosed tank containing a liquid of density rho has a hole in its side at a distance y1 from the tank's bottom. So this is at a distance y1 from the tank's bottom. The hole is open to atmosphere and its diameter is much smaller. Okay, so its diameter is much smaller than the diameter of the tank. The air above the liquid is maintained at a pressure P. Determine the speed of the liquid as it leaves the hole when the liquid's level is a distance h above the hole. So this is at a distance h above the hole. This is y1. This is y2, the surface level of the liquid. And here we have atmospheric pressure P0. Okay, now for the continuity equation, we have the volume flux A2V2. So this is our point 2 here, that's the surface. This must be equal to A1V1. So the dV dt is a constant. So this is our continuity equation. However, we have an important statement here. The hole is open to atmosphere and its diameter is much smaller than the diameter of the tank. So the hole diameter is much smaller than the diameter of the tank. So this is saying A2 is much greater than A1, right? So this diameter is small compared to this one, so that means the area is much smaller. Therefore, we can say that V2, which is basically using the continuity equation A1V1 divided by A2 is approximately 0. Okay, so we can neglect the velocity of the particles as these particles leave this hole because it's rather small. So that's what it is saying. Now we write Bernoulli's equation this time. So in the Venturi tube, we didn't have a potential energy term, remember, so these are all at the same level. Here they're not at the same level, but we can neglect the kinetic energy of the particles at the surface. So here we can write, for point 2, we have pressure P plus the potential energy term rho gy2, and we neglect the kinetic energy. This must be equal to the pressure at point 1, which is atmospheric pressure, plus potential energy term rho gy1, plus the kinetic energy term 1/2 rho v1 squared. So we have written Bernoulli's equation for this setup. All right. So if we take P0 to the left-hand side, P minus P0 plus rho g, now I take y1 term to the left-hand side, rho g y2 minus y1 this is equal to 1/2 rho V1 squared. So that's basically what I need to get, determine the speed of the liquid as it leaves the hole. So I obtain V1 is equal to, here is 2P minus P0, that's the gauge pressure, divided by rho, the first term, plus I have 2 rho gy divided by rho, so that becomes 2g, and y2 minus y1 is equal to h. So this is 2gh, and I have to take the square root to obtain my final answer. All right, so and this result is basically known as Toricelli's law. Okay, and what happens if this pressure is P0? So if this was open to atmosphere, in that case, if P is equal to P0, I would obtain V1 is equal to square root 2gh. So if I have the same pressure on both sides, that's basically corresponding to free fall case. I have 1/2 mv square is equal to mgh. So the kinetic energy turns into potential energy turns into kinetic energy. So that's basically free fall, where I have no contribution from pressure. Okay, now an important application of Bernoulli's equation is basically this atomizer. So this is something you use very frequently. If you have a perfume bottle, it consists of an atomizer here. So we basically push these air particles inside with a very high velocity. So this high velocity implies low pressure. Remember Bernoulli's equation. When we increase the velocity, the pressure is going to decrease. So what happens if the pressure decreases here? We have a high pressure at the bottom of the liquid and we have a low pressure on top. So these liquid particles will be forced outside, and we will see that they will come out as we do this compression of the atomizer. So a stream of air passing over a tube dipped into a liquid causes the liquid to rise in the tube and leave the pipe. So that's basically frequently used in perfume bottles. Okay, so to summarize, we have talked about Bernoulli's equation. We can see that Bernoulli's equation is just a result of change in the mechanical energy of the system due to the net work done by external forces. And when we consider the pressure of the pressure applied at the point where these particles are entering a pipe and pressure at the point when these particles are leaving a pipe, the pressure difference P1 minus P2 is equal to 1/2 rho V2 square minus V1 plus rho G Y2 minus Y1. So we have a kinetic energy term and a potential energy term. And this basically tells us that the pressure at a point plus 1/2 rho V square, rho is the density, V is the tangential velocity of the particles, plus rho Gy, the Y is the distance with respect to ground, is a constant. That's Bernoulli's equation. And as the velocity of the particles increase, the pressure will decrease. And as Y increases, pressure will decrease also. And when at rest, when the particles are at rest, P plus rho Gy is a constant. We have seen one application for the Venturi tube where there is no change in the potential energy of the particles, and we know the pressure differential between 2 points, 1 and 2, and we know the cross-sectional areas in point 1 and 2. We can calculate the velocity of the particles at point 2 Using the continuity equation where the volume flux is a constant, so A1V1 equals A2V2, and using Bernoulli's equation with no potential energy term, P plus 1/2 rho V square should be a constant for this tube. And another application we have seen for Toricelli's law. Here we have an enclosed tank where there is a pressure P on top and the pressure outside is the atmospheric pressure. We have a very small hole compared to the surface area of the liquid, which allows us to neglect the kinetic energy of the particles that are on top. And writing Bernoulli's equation, basically we can neglect V2, so we have only potential energy term and pressure for these particles, but here we have both potential energy and kinetic energy terms, and this allows us to write the velocity of the particles leaving the hole. So the speed of the particles as they leave the hole will be given by Toricelli's law. And if the pressures are the same, then this just turns into basically potential energy, mgh, turning into kinetic energy, 1/2 mv squared. That's a free fall. We have seen that this has important applications. For example, the atomizer in perfume bottles. If you compress this, you have air particles causing an increase in the velocity of the fluid particles here that decreases the pressure, and liquid will be forced from the bottom to top due to a pressure differential between the top and the bottom.